In this video, we are looking at H8 and some lessons for you from me after grading it. And we have a file to remind us of these things, and we'll look through our answers. Okay, so first, some notes about worst case versus best case running time. Okay, so some algorithms have the same exact best case and worst case, and this is true for selection sort. So selection sort is going to have the same exact running time always, just by the way it works. So how does selection sort work? I can say just a little bit. So let's say it has some numbers x1, x2, x3, x4 up to xn. Okay, so the first step of the algorithm is it checks each number to find the smallest one and puts it at the front. If the list is already sorted, the algorithm doesn't know that. It doesn't take that into account. So it just looks to see which one is the smallest, and if it happens to be already at the front, then it stays there. And that's going to be the same no matter whether the list is sorted or not. So it's not part of the algorithm to actually do anything different. All right, so this is an instance where the running time is always the same. A difference is with linear search. So linear search, you're looking for some number. If the number you're looking for happens to be at the front of the list, then it only takes one step. You're done. You found it. And the same will be true of binary search. Where does binary search look? Binary search looks at the middle of a list and assumes the list is already sorted. Okay, so if the middle item happens to be the one you're looking for, you're done. It took one step. So both linear search and binary search have a really good best case running time. So there are some instances where they are really fast. Okay. So sometimes it will be the case that the best case and the worst case running times are the same, and sometimes it is not. Okay, so that is best case and worst case running times. It just depends on the algorithm. Now, binary search. Some people had the running time as n/2. Some people had the running time as log n. So the actual formula is log 2. I don't know if there is a log 2. No. So it's a logarithm with a base 2, which we can get. Well, if we just do it like this, it's a log. It looks like it's doing base 10 log. Logarithm is what power do I have to get this number? So what is the log base 10 of 1,000? It's 3 because 10 cubed is 1,000, but I want the base 2. So one way to do that is you take your number. Say we take the log 10. Okay, so this would be 2 to the 3.32 power is 10. Which makes sense because 2 cubed is 8 and 2 to the 4th is 16. All right. And if you apply that to 1,000 and 1,000,000, then you get numbers like this. And that probably is a good approximation of how many steps you actually got in the algorithm. Because it's when you do the analysis of binary search, the formula that comes out is log base 2. So the confusion with n over 2, I think people are thinking that it's n over 2 because there's an n over 2 in the analysis, but what really happens is you look at the middle, and n over 2 is how many numbers are removed after looking at the middle. So you look at the middle number, and either you don't have to look at the top half because your number is smaller, or you don't have to look at the bottom half because your number is bigger. Either way, you got rid of half of the items, but you only looked at the middle. You only looked at one step. You only took one step. Okay, so this n over 2, it's every time you look at a number, you get rid of half of the remaining items. And if you work that out, then if you do that this many times, you're only left with one thing to check in the end, if you didn't already find what you were looking for. Okay, so that's binary search. If you put just equals log of this, that does not give you the right answer. It's off by this amount, this 3.3. So each of your values would be 3.3 too small. Okay, another thing, let's see what's next on our list. We'll just keep going. Measuring running time with the time command. So I'm going to go and run this. This is H8. So n equals 10. And this is the printout that we get. And what do these three different numbers mean? So this one here is how much time actually passed on the clock. So from the beginning of when I started the program until when it was done. That's what that number means. This one here means how much CPU time did my program actually use. So if there's a bunch of stuff happening on the system and it's really busy, it could take a long time on the clock, right? It could be a while until my program finishes, even if the computer's not doing anything for me because it's doing other stuff. So this number here will potentially be smaller. That's how much time did the CPU actually do my stuff. And this one is how much time did the operating system have to take for my program. So that would be writing characters to the screen, reading files, things that the operating system has to do. Okay. Another difference between the real and the user, if I have, let's say that I'm doing 4 cores. I have a program that's using 4 cores. We haven't done that in this class, but if you do, then this number will show adding them all up. So there you could have a real time of, let's say 15 seconds, and you could have a user time of 52. That we had 4 cores, and that's how much time, if you add up all the cores, how much time they spent. Okay, so those are those 3 times. Many people asked about if we run this. So if I run it for n10 and n100 or 1000, I have the same user time. So it's not different, or it even could be, that this one was lower. Some people were seeing that when you change n to go higher, these numbers should go higher, but they were either staying the same or going lower. And the reason is because the time is so small. So anything less than a second is just nearly instant. And especially these are so small that that's just kind of the time it takes for the program to get started and to stop. There's no real computation going on. So you have to get to the ones where it's taking longer than a second. So like this one here, we've got half a second at least. So that's a big enough running time that we should see with a larger input size, it'll actually get bigger. Okay. There were some people that came up with slightly different answers for the formulas, and I normally gave this to you. So the formula in the reading on Khan Academy was like this. So you had our n there times n minus 1 divided by 2. Depending on where you look, you might also see the formula n times n plus 1 over 2. What was that? 8. You get different values there. And depending on how you count operations, either one of them could be correct. Now, one of them is more correct than the other, but when we look at running times, we'll often say that it's just big O of n squared. Because if you multiply this out, you have n squared plus n all over 2. So half n squared plus half n. Or here we have half n squared minus half n. Either way, the n squared is kind of the part that's the most important. If we look at these, they're sort of both growing quadratically. So then later on, when we look at lots of different types of algorithms for things, this is the common way that we'll see it. As a first approximation, how does the program do? This amount of detail, it isn't super important which one of these you're thinking of. They're both correct in this case, depending on how you count operations. But both of them are called big O of n squared. Okay, long-running programs. So some of these programs took forever, so they never finished. So you might have put something like greater than 2 minutes. You waited for 2 minutes and then you killed it. If it ran for greater than 2 minutes and you didn't get a step count, so you'd have to put here don't know. But for the formula says, you can run the formula. The formula says something, you just didn't get a actual running time when you ran it because you had to kill it. So this here also you could say, well, let's see, 499 trillion. So if the formula says it's going to take 499 trillion steps, how long would it take an actual computer to do it? Computers kind of do a billion things per second, maybe. So if it's taking 499 trillion, that's like 500,000, or that's like 500 seconds at least. So maybe you have to wait that, maybe longer. It just depends. Okay, so if you have a formula, you still should put it in there. Okay, and anagrams. So if you wanted to test on actual words that have anagrams on this one, let's see, 10-letter anagrams. And there are some. These aren't necessarily all in our list of words, but some of them are.